is Jakub Sebek, and with my colleagues from the Brno University of Technology and the Academy of Sciences of Czech Republic, I would like to show you the work which is actually the study of the impact of the specific fracture energy inputted into the numerical models for the quasi-brittle materials. As you heard from Hanna Šimonova, the fact that the quasi-brittle behavior is quite difficult. So we need to somehow test these materials on the test specimen subjected to different test configurations. Okay, and the pointer. Yeah, thank you very much. So once more, the quasi-brittle fracture is complicated. So the testing, these materials are necessary in different loading combination to obtain so-called fracture parameters, which are also and always dependent on the so-called fracture process zone, which is a zone in front of the propagating crack, which can characterize the quasi-brittle embrittlement of the material. And the fracture parameters and also the fracture process zone is dependent on the specimen size, the shape, and the boundary condition. So we speak about the size, shape, and boundary effects. But if we would like to simulate again the quasi-brittle fracture by numerical tools, we need to choose the proper inputs. And usually you know what you would like to obtain from the numerical calculational models. It's not always what you get. So it's very important to choose the proper inputs like the specific fracture energy. So our aim was to study the impact of the specific fracture energy, input it into numerical software, and the dependency was on the value of the fracture energy, total fracture energy obtained from the numerical results. And we wanted to consider the fracture failure of the test specimen, so we chose the commercial nonlinear software which can predict the quasi-brittle fracture. It's called Athena 2D software, and we choose the test configuration of subjected to three-point bending test. We chose the geometry from the comprehensive study done by the Christian Huber and his colleagues from the Northwestern University from the 2011 to 2013. This study consisted of almost 170 test specimens which were created from the one batch of the concrete, and 128 of these test specimens were notch fracture specimens subjected to three-point bending, and the initial crack length was between the 0 and 30% of the total width of the test specimen. The ratio between the smallest test specimen and the largest test specimen was 12.5. So in this step, you can see that the test geometry was for the 4 basic test specimens. The smallest one has got the width of 40 millimeters. The largest one, the 500 millimeters. The same breadth was chosen for the all test specimen, and for purpose of our study, we choose the 3 basic initial crack length. So to summarize this part, actually we choose the 4 sizes of the test specimen with the different width of the test specimen and the rest of the parameters like the length and the upper span of the specimen. And we chose the initial crack length in 3 basis sizes, like 0.075, 0.15 and 0.30, so 30% of the width of the test specimen, with the same breadth for all test specimens. To compare the impact of the specific fracture energy, we need to set down 2 basic fracture energies. One we call the theoretical fracture energy. It's just obtained from this simple formula where the GF is a specific fracture energy inputted into numerical software, so also inputted into this formula, multiplied by the division of the crack length and initial crack length, and also multiplied by the breadth of the test specimen. The second one was the numerical fracture energy, and it consists of the work of a fracture which was obtained from the loading diagrams of the all variants of test specimens with the various initial crack lengths, and from these diagrams we recalculated them into the resistance curves using every point of the loading diagram and recalculated into the equivalent elastic crack and making the resistance curve. For all variants, we chose the maximum relative crack length, the total crack length, alpha to be 0.7, so damage of the 70% of the width of the test specimen. Okay, now the creation of the numerical model. As I told you, we choose the commercial one, finite element nonlinear system, which can predict the fracture behavior of our models. It is based on the orthotropic theory of the smeared cracks with the implemented crack band model, so simply the cohesive raw model was inputted into the software. It consists from the various nonlinear material models to like the plasticity, fracture and damage. So all models were created as the plane models with the same material constants. For the quasi-brittle material, we choose the 3D nonlinear Cementeos 2 material model, which is in the library of this software. We chose the material properties like the study from the Hoover and his colleagues. So the Young's modulus of the concrete was 34 gigapascals, Poisson ratio 0.172, fracture or the tensile strength, fracture behavior, I think it's equal, so the tensile strength was characterized by the 5.4 megapascals and the compression strength by 49 megapascals. We use the Rodrigues exponential softening for the finite elements, and basically we choose the 3 levels of the specific fracture energy. Therefore the one, or the middle one, was the 70 joules, then the lowest level was 7 joules, and the largest was 700 joules. The steel platens for the free-point bending, the specimen was free-point bended, was the steel, or the steel platens were formed by the elastic isotropic material model with the Young's modulus 210 gigapascals and Poisson ratio 0.3. We used the contact elements between the steel platens and between the concrete part of the specimen, and we make a calculation with the Newton-Raphson nonlinear method and with the increment of the deformation into the head of the steel platen. So now the results, you can see the loading diagram for the larger test specimen with a width of 500 millimeters. On this axis, you can see the displacement of the points, middle part of the test specimen, and here the peak load of the specimen for the three basic levels of the specific fracture energy used. So you can see it strongly varies by this value. So if you can see it for the smallest or the little level of the specific fracture energy, the behavior of the test specimen is more brittle. So on the other way, with the usage of the largest level of the specific fracture energy, you can see more ductile behavior. And of course, for the default one, you can see more quasi-brittle behavior. And this is similar to resistance curve obtained from this. So you can see the strong dependency on the specific fracture energy used. And it also can be seen here in this graph of dissipated energy, so the total fracture energy obtained from the resistance curves, transformed from the loading diagrams, and it's simply the value of the energy I show you, the numerical energy obtained from the areas under the loading curves. In this line, you can see the initial relative Craig length. So this graph is divided into three parts, basically related to the this initial notch for the all test specimens, from the smallest one to the largest one. So as I told you, dependency on the specific fracture energy. It's in joules, so this comparison. The smallest fracture energy can be seen for the biggest initial notch used. So same trend should be here in this graph, where this dissipated energy belongs to the theoretical part of the fracture energy, which was just simply calculated by the formula where was the level of the specific fracture energy. So the same trend should be seen. And this is a deviation of these two parts I showed you. So of two basic energies, the numerical one obtained from the area and the theoretical one obtained from the formula. You can see the strong fluctuation of these results, and as was seen, yes, if there is some dependency on elastic fracture energy, it should be also in a deviation of these two values. The largest deviation is for the biggest test specimen with the lowest initial notch. It's more than 120%, and the lowest deviation is in a case, two times in a case of the second smallest specimen with the width of 90 millimeters, also for a smallest initial notch, and the middle one with the value 0.15. So actually, if you would like to numerically obtain some results to fit the real experiments, we need to actually choose a proper specific fracture energy. So we need to take care about it. So let me conclude our contribution. As I told you, a significant dependence of the maximum achieved loading force on the value of the specific fracture energy was observed. Also, obtained results showed a strong dependence of the amount of dissipated energy during the fracture of the value of specific fracture energy, which we considered into calculation. So, setting of the proper value of the specific fracture energy is crucial when we would like to do more complex fracture analysis, because we would like to visit the results. So this is acknowledgement, and I thank you for your attention.